some differences between the two observations. So I've conducted this work at Bryn Mawr College, which is just outside of Philadelphia, and also in the audience is Bob Eakey, who's worked with me on these experiments since being a PhD student and also since he's become a faculty member. So I'll begin by talking about these long-range configurations, which we were studying in general, and in particular about the ones that have the ion pair character, our experimental arrangement, and the kinds of observations we've seen. And we have focused on an energy region that's very near the threshold for neutral dissociation in the molecule, the third dissociation limit. So there's been a lot of work in a kind of adiabatic picture, mostly Wolniewicz and co-workers, Stazveka and Wolniewicz in particular, in calculating the molecular potentials in hydrogen. And we were focusing on, as Frederick just reminded us, the outside of the EF state, the outside edge of the 3 state, and then further up, this whole series of sigma states have at internuclear distances greater than 10, this ion pair character. And Tom's question, referred to, how deep do you go on this ion pair curve and call them ion pair resonances? And there's this transition from the definition that Wim talked about of ion pair character, of the vibrational states of these molecular curves, to this region up here where you're really starting to have Rydberg character full states. I'll show you some results from Adam's work that kind of illustrates that, where up here the quantum defects associated with a heavy Rydberg type model, they're still changing, but they're starting to level out up here. So we'll get back to that. We were really, I would say, inspired by some of the work by Wim's group and really wanted to explore this region kind of in a naive sense, wondering if we could detect resonances in this outer well of the 6th state. And what would they look like and how would they relate to the ion pair series? So that was our motivation for looking at the states in this region near the n=3 dissociation threshold. This is very similar to the slide that Wim showed, describing the relationship between molecular electronic Rydberg states, which was the reference point I was coming from, and these heavy or vibrationally kind of coupled ion pair states in the heavy system. So I won't go over this too much. Wim already described how the electronic molecular Rydbergs are a lot like atomic ones because of this mass scaling effect, which is only 1. But if you go to the heavy system, as he described, the mass scaling is almost a factor of 1,000. And so the whole behavior of the Rydberg series gets stretched out, and all the other parameters get scaled with this mass term. And to the degree that you have a composite particle in H-, you get a little bit of a difference from a pure Coulombic interpretation because of these effects. But for large enough internuclear separations, you are going to have a pattern of energy levels that look Rydberg-like. So here's our excitation scheme. Let's see if this is clear enough. We are going to go through, as our intermediate state, the EF state, V=6 level. We populate that state by doing a 2-photon absorption from the ground state of photons at 193 nanometers. It will show you how we make those. My career in making 193 nanometer photons goes way back to when I was working with Ed Eiler, when BBO crystals were first invented by the Chinese. And then from that intermediate step, we take another dye laser and resonantly produce ions. And I'll describe later, not only we produce ions in 2 distinct ways, which I'll describe later, which gives us a little bit of a window into the dynamics of how we're detecting these ion pair resonances. But like Wim described, one wouldn't expect to actually directly populate ion pair states because of the mismatch of the Frank-Connon regions. So we also are relying on this deeply mixed nature of the resonances up in this energy region, requiring us to actually have couplings between these long-range configurations and short-range configurations. So essentially it's a REMPE experiment, and we're able to select out a single vibrational and rotational intermediate state that allows us to do kind of a state-resolved experiments. And because the EF state energies are known very precisely through Wim's work and earlier Ed Eiler's work, we can connect these energies with fairly high precision down to the ground state. Okay. This is a slide that just reminds us of, it's helpful to go through these quasi longer range states to get some wave function out at large R. And this is just an example of the Frank-Connon overlap between the EF state and the B state. We originally had planned to do these experiments not in the two-color rendition, which I'm going to describe here, but we had planned that we would need a three-color experiment where we were going to stepwise go through a high-lying B double prime B bar state to try to access the ion pair states in order to build up some, oscillator, transition strength as we went up the energy scale. But in the end, as I'll show you, we began to see signature of the ion pair states even in the two-color experiment. So here's a schematic of our experiment, and there are kind of three sections to look at here. We have over on this side our scheme for creating 193 nanometer laser pulses, and on this side another YAG pump dye laser system to create the probe laser, which we call the probe laser, which actually brings us up to the states of interest. And then in the center you'll see a schematic depicting how we actually detect the ions. We have a vacuum chamber that runs a pulse valve hydrogen beam and a short time of flight mass spectrometer where we have some field plates that we pulse on that will accelerate the ions we produce through photoabsorption towards a channel plate detector. And we just use a simple boxcar averager to integrate the signal as a function of scanning the probe laser. We introduce a delay between the laser that produces the EF state and the laser then that excites from the EF state, so we can isolate the ions that are produced just by the second laser. What else to say? We use a calibration scheme that involves tracking the transmission through an etalon that allows us to linearize our data scans and then make measurements of the energies relative to elements in an optogalvanic cell. That's how we do the energy calibration. So let me just mention, we in the experiment I'm going to tell you about, we double the output of a dye laser running in the red to get probe photons. And we generate the 193 by mixing the fourth harmonic of a YAG at 266 with the output of a dye laser that's been pumped with the second harmonic of the YAG in a BBO crystal. And we get about 100 to 150 microjoules per pulse in this scheme. And with a lens, we have plenty of, this turns out to be plenty of light to photoionize, excite and photoionize the molecular hydrogen. Okay. Here's an example of the time of flight signals that we get. So we're looking at the voltage signal on our detector as a function of time after the probe laser. And you'll see when we pulse a field on, we accelerate the ions through a short drifting region, and then they arrive at the detector at different times based on how much the field has accelerated them. So you'll see the H plus signals arrive sooner than the H2 plus, and in this case the separation here is because of the pulse delay of the two lasers. And we're interested in this H plus signal. Most of the spectra I'll show you are from tracking the H plus signal right here that's from the signal plus that's from the pump and probe processes to create those ions. And there are two ways you can make H plus in our scenario, and this is very important for understanding the mechanics of what's actually happening. So let me take a few minutes here. Here's our EF state. We come in with our probe laser at some energy that's very near this threshold. And we can immediately photoionize into H2 plus, which then can dissociate. The molecular ion dissociates, creating H plus with a fair amount of kinetic energy. Okay? That's process A, down here, up here. We create a bound resonance, and that photoionizes and creates a molecular ion that then dissociates with a lot of kinetic energy. Process B is we populate this energy region, and the system fragments into neutral dissociation, and then we ionize the H atom in the n equals 3 to produce H plus. That's described here. We really directly excite the continuum, or states coupled to the continuum, and then we photoionize the neutral H atom and produce H plus. In this scenario, most of the kinetic energy is taken by the electron, and there's very little kinetic energy in the H plus fragment. And we can see the different components of it within the time of flight signal. The H plus pulse we see has some structure to it, and we can distinguish between the fast H plus and the slower H plus. So here is an example of our measurement of this energy region that's very close to the n equals 3 dissociation threshold and the kinds of resonances we observed. And when we first started to see this, we were pretty excited and encouraged by the UBACS result that perhaps we too were seeing this with only our two-color experiment because of this mechanism of coupling to the short range. In our initial kind of analysis of this, though, we were a little bit perplexed because here's an example of the mass-scaled heavy Rydberg prediction with a 0 quantum defect. And while we were kind of encouraged by the spacings kind of being more typical of a heavy system versus the spacings of an electronic Rydberg, as you can see we've plotted up here, we found it difficult to consistently fit across this broad energy region this type of heavy Rydberg behavior, until we saw Adams' paper, which analyzed the UBACS results, which showed that actually at these principal quantum numbers, this fairly low for this system, the quantum defect is actually changing really rapidly. And so we shouldn't expect to get a single quantum defect type series. So we'll get a little background today, okay? Well timed. And I should say, in reference to Tom's question, I think the notion of when does this heavy Rydberg system really turn on as a heavy Rydberg system? And this value of about 130 principal quantum number really corresponds to internuclear separation between the H plus and the H minus, around 12 atomic units. So there's a way in which the rapidly changing quantum defect here is because they really aren't very Rydberg-like yet in terms of energy. Well, it turns out below here, below this dissociation limit, we don't see clearly signature of ion pair states. And the reason why in our experiment is we're principally seeing these seeing these features via the coupling to the neutral channel. So we have to be above this threshold to see them. So let's move forward. Here we go. So subsequent to this result, Adam and I had a chance to meet and interact, and Adam took his kind of full adiabatic calculation of the sigma series in molecular hydrogen with the dissociation channels coupled in, and computed the resonances due to these states, many of whom are ion pair character at high enough energy, for our particular symmetry of states, and he also included the sigma interlopers that occur here. And this is his result. Here he's plotted our experimental data in green and his theoretical predictions in black, red, and blue according to angular momentum, and he's captured the trend by plotting quantum defect as a function of energy. And you can see, and down here is the dissociation threshold, you can see the rapidly varying quantum defect, and in addition you can see how the series is perturbed by these short-range interlopers. These are vibrational levels of sigma states v equals 10, 11, and 12 of the 6 potential energy curve. And you can see, there's a lot of scatter in our data, and there's certainly a way to assign our data such that you get this turnover. But the details up here, there's lots of things to still understand. And so there's a similar plot as this one to the data that Wim talked about. But what's interesting in the Gerada series, the interlopers are different, and the rate of change of the quantum defect is also slightly different, especially up here. We see this kind of turnover, whereas I think it's the case in the Gerada series, it continues to go up more smoothly. So there's some interesting differences between the two manifestations of these states in the molecule. So what I thought I'd do is try to say, well, and so this is really a nice kind of confirmation that I think we are seeing a signature of these states, but there are 3 areas where we want to go deeper and see if we can challenge the theory and understand the effect of the ionization couplings that have yet to be put into the theory, but were so important for the Gerada series and for our series as well, you'll see. So I want to look at the threshold. I want to look at one of the regions where these interlopers show up, and then I also want to show where there's a nice region in here where all is pretty well, just to give you a feel for the range of what this data is exhibiting. Okay, so first what I wanted to show you is in this mid-energy range where what is the quality of Adam's theory and the data we've collected, the agreement, which is quite astonishing, I think. So in green are Adam's calculation for j equals 1 levels of these series of states in this energy region. And in the colored spectra are data we've taken by going through 3 intermediate states, the j equals 0, 1, and 2 states of the EF. So they represent, for example, the blue spectra here would be an R transition from j equals 0 to j equals 1. And you can see we've got some interesting shapes to these curves and different wavelengths and also different kind of envelopes happening. But the agreement with where the resonances are showing up is quite impressive. And you can see as a function of angular momentum, we'll have different envelopes and definitely a trend of increasing line widths in the series as you go up. So this is very encouraging, I think. And now what I want to do is bring our attention back to the potential energy curves in this region, because I want to show you an example of the spectra we observe where we're coupling to some vibrational levels of this inner well 6 state. So this is a figure from Adam's paper where the potential energy curves are shown, and these curves, of course, were calculated by Stejewska and Wolniewicz, and are part of the calculation that Adam does. He'll probably say a few words about that later when he speaks. But what he's done is calculate the resonances in this energy region, and not only the ion pair type states, but also the rho vibronic levels that occur on the sigma states in this region as well. And some of them have very short range character, and some of them, of course, have the long range character. So there's one particular example in our spectra that seems to illustrate one of these interloping interactions. So what I've shown here is our H+ signal as a function of energy, and based on the theoretical work made assignments to principal quantum numbers in the ion pair series and shown where we're getting a perturbation to the regular series that seems to indicate the presence of this particular interloping inner well state, the V equals 6, sorry, the V equals 11 vibrational level of the 6 sigma state. So this is another interesting opportunity to test the theory and with the experimental observations we're seeing. All right, the next example, and here's a table of energies that show possible assignment of various interlopers. So the V5-9 level, the V6-8, 9, and 11, which is the one I just showed you. I would say these are the status of the comparison at this point, and as the ionization channels are added, and as we kind of refine the understanding of the couplings amongst these states, we may see these agreements even improve. I think that's a fair statement to make. Great, and so you might ask the question, how do we know, so there's this observed set of resonances. I think it's important to point out any particular resonance, because the mechanism has to be a highly coupled one, how you label a particular resonance becomes a bit of an art form, right? And Adam came up with a nice scenario where he compared the adiabatic energies on the 6th state to help identify which ones were closer in that picture to the results of his work, to guide us in kind of labeling the particular resonances compared to this kind of single, I guess, a single state type of interpretation. Okay. So the next comparison we can make is to look at the line widths we're observing. We definitely see the line widths varying with angular momentum, but we also see the line widths in the series varying with energy and their proximity to the interloping states. And so this is a wonderful outcome of the theory, which really shows this is the line width of the resonances as a function of energy, and the line widths expand and contract, get wide and narrow in an oscillatory fashion throughout the series. Very interesting result. And in particular, at the interloping states, that oscillating kind of pattern in the series is disrupted. So what I've shown here is we see this significant variation in line widths, and I've just zeroed in on this energy region and given you a flavor of the observed line widths as a function of energy. And I think you can see there's some error bars here. And indeed, we see the variation of line widths that from relatively narrow to broad through this region. And this is the region that's through the V equals 11 interloper. So there seems to be some good qualitative agreement there of the trends in line widths. Okay, I'm going to come back to this. My final kind of example of interpretation or comparison is in the threshold region near the n equals 3 threshold. And for that, I wanted to remind us about the dynamics here. So we're exciting into this energy region that's just above this threshold, and we're hitting some of these ion pair resonances. But the principal mechanism through which we see features that match the ion pair is through the continuum. It's really the H atoms that are being ionized. It is that component of the H plus that shows the features that correspond to the ion pair. Correspondingly, if we excite a short-range state or a harmonic Rydberg, we'd expect to photoionize that and create very fast H plus, right? And so if we can distinguish between the type of H plus we're actually monitoring, we might get some insight into whether it's predominantly a long-range ion pair type configuration or predominantly a short-range molecular Rydberg type character. This is a story that's in progress because in our early observations and our early understanding of what we were seeing, we were pretty excited about the correspondence between, this is a spectra near threshold, we were pretty excited about the correspondence of some very sharp resonances with predicted energy values of this outer well 6 state, which was one of our motivations for doing the experiment. I think now that I have at least a more complicated understanding of the dynamics of these states, it's not clear whether such an assignment can be made with 100% confidence. But let me tell you what we know. First of all, in this region, you've got sharp resonances that lie below the dissociation threshold. These happen to be high vibrational levels of the D state and high vibrational levels of the B double prime B bar state. But above threshold, we see a continuum, and embedded in that continuum, we also see some broad features. And in addition, we also see a couple sharp lines that have at face value seem to have a different character. And these particular were very suggestive because they happen to match very well the adiabatic energies calculated by Stejveka and Wolniewicz for the outer well of the sixth state. Here's what they predicted, 640, 676, 618, and here's where we observed these sharp features, 641. So we were like, wow, I wonder if these are those states. Then we understood that those states, even though they're in the outer well of the sixth state, let's see if we go back to that. They're right here, V equals 0, 1, and 2. They still have this strong ion pair character, and Adam's calculation should pick them up as well. But so that's what we see, and we're trying to understand. Here's a closer look at our experiment. Now I'm showing you the three intermediate angular momentum states, EF 0, J equals 0, 1, and 2, and I'm showing you the same energy region across the threshold marked by this line. And you can see in the Q0, you've got the onset, and then you've got these two sharp lines that are the two I showed you before. And then you see the beginning of the series starting as a set of really broad lines. And here, this is reminiscent of WIM's results, where you're seeing interference between the continuum and the resonances, creating these asymmetric shapes. And then this continues on and marches on in the series. So a couple of general observations. You see the rotational trend as you go up in rotation, but you also see some other sharp lines in the near threshold piece of the spectrum. And I would say it's the interpretation of this near threshold set of features that will be a really kind of, that I think is a kind of critical connection to understanding the details of the couplings that is A, explaining how we make them, and B, explaining how we detect these resonances. It happens to be the case that there are the n equals 14 NP1 electronic Rydberg, the n equals 12 NP3 Rydberg in these levels. We need to understand in more detail exactly where those p states might lie. And here's another piece of the puzzle. If I do a gate on my time of flight signal that really captures these early H+ signals, I can kind of preferentially detect fast H+, which means I'm preferentially detecting H2+ ions that then fragment into H and H+. So not the neutral channel, but instead the short-range molecular ion channel. And this, again, this is a scan over the energy region just above threshold, which is given as 0 here. And I've got 3 scans here. The top are the raw data. This is the H2+ spectrum. You can see it's showing, because we're above the IP, we're seeing a depletion spectra in that spectrum. And then I've got the H+ detection. It's the fast component. And you can see resonances showing up as positive signals in that spectra. And then here I've plotted the difference between the two of these, which in some sense should represent the neutral channel, meaning it's the difference between H+ and H2+. And when I detect the full H+ component, it looks very much like this. But interestingly, these two peaks are made by the mechanism at short range, creating H2+ that then dissociates. But even more fascinating is this peak is a new peak. This is the peak that's at 640 in the previous spectra. So this is evidence that we have electronic molecular Rydberg type character in these states. Thanks. And so my takeaway message from trying to parse this out is there's a lot to learn to do some more work by separating out these two fragments. And of course the right way to do this is to do what Wim hinted at the end of his talk, was to use a velocity map imaging type detector that would allow you to parse out all these channels. You really could tell where everything was coming from to sort out the assignments of these states. So this is a promising direction, but it's clear this near threshold behavior is complicated and we have more work to do. And one of the things we were focusing on most recently is understanding this 6 well and the this avoided crossing between it, the 6 state, and the 3 state, which is what creates this outer well, and the fact that there are adiabatic and non-adiabatic corrections to these curves, and how that's going to influence the structure there. Given that you would think if you had a state here, it would be pretty isolated. So A, how do we make it, and B, how do we see it? And one pathway is if these states are tunneling out into the n=3 continuum, there's the issue of how strong is the tunneling and what lifetimes would that create. And one of the contributions to this kind of story, also by Wim and his group, was back in 2003 when they actually calculated tunneling rates as they were trying to get a handle on why they didn't see these resonances when they looked near the threshold. They were using a different excitation scheme, but still raised the question, what was the reason why they weren't able to see any resonances? And one possible explanation were the resonances were just too broad to discern in the background. So we've got that bit of information. We've got the adiabatic energies that are matching up pretty well, and potentially the full calculation by atom may help us resolve these kind of competing storylines. So that's an area that we're working on now. So let me wrap up with just these 4 kind of summary statements that I'll leave you to read. But I think the highlights of what we've been able to show is indeed we're seeing the ion pair type features in the neutral dissociation of molecular hydrogen. We don't have a good grip on the exact mechanism of how we're creating them and then the mechanisms for detecting them, but that's part of this conversation with the theoretical calculations, which should help us get a handle on that. We're excited that some of these levels we're seeing near threshold may be arguably associated with the 6-state outer well, and this is kind of a benchmark in that these are one of the longest range stable states observed in molecular hydrogen at R equals around 30 atomic units. And we're seeing good evidence of these interlopers, which again, the coupling between them and the series will really help to pin down the viability of the theoretical calculations. Okay, I'll stop there and see if we have any questions or discussion. Thanks. Sure.
Any questions for Elizabeth?
Yeah, Ralph.
Yeah, so in the predicted line width variations where you compared the spectra, I think that's right. I guess I probably missed what J state were you, I mean, your experimental data comes from which J state of the EF?
So this data is from J=1, so presumably it could have either J=2 or J=0.
Right.
There's a sense that the R branch would be stronger. But in the experimental data, the J=0 and 2 levels would not be resolved within these line widths.
And the reason the R branch is stronger is just sort of Hahn-London?
Just the Hahn-London
factors.
Yeah.
Okay, right. And I guess also, so is the bottom data the entire range you took? Because I kind of got the impression that your range was a lot broader than that.
This is just the range. This is the range of this spectrum.
Right.
So I just actually reported the line widths for that particular range. We haven't analyzed the line widths for the rest of the series.
All right. Okay.
we suffered from the signal to noise problem too. Is the spectra are very noisy, and to really get a good set of error bars on the widths, one has to do multiple measurements. Yeah.
I guess that would be a question from me. Do you see Do you see the possibility to significantly improve the line width measurement or resolve the line width more accurately in experiments?
Yes. There's a way in which, to date, I could characterize our work as kind of this broad survey of the energy region. So there's an opportunity to really focus in on an area and get multiple scans and do, with enough kind of accumulated signal, do some good fitting to the curves to be able to report the parameters with smaller error bars. Yeah.
So these special, very long-range resonances. Yeah. So we have looked for it and haven't seen it. So, but you see them decaying in h n = 3.
Yeah.
Okay. So in our experiment, we tried to detect them with the green laser, assuming that it would be n = 4. Otherwise, we wouldn't have seen them. That's a difference. Of course, we did this Landau-Zener calculation and showing to ourselves that we couldn't have seen them, but maybe that's not the proper way to do it. But the experiment is different then also.
Yes.
That's encouraging to know.
So
if you want to claim your assignment.
Yeah. So one of the questions, Wim, was, here we go. In this diagram, I was curious to know from where you were with your 532, just a quick kind of understanding of whether you would have been, I guess you would have been. It's hard to know whether your 532 would have actually put you on this H2 plus curve, which might be important to see the 640 resonance, for example. If that question makes sense.
I can show you the scheme. It's in my computer, but we'll discuss later. Yeah.
Any other question? I think that would be the final question.
It's more a suggestion, but I don't know whether it makes sense. For your setup, you don't have this velocity map imaging, but you could probably delay the extraction field. Because you said you get fast protons and slow protons. And maybe just by waiting a few nanoseconds, you would enhance the slow proton signal. That would make the separation easier.
Thank you. So,
I had a question about the folks who were worried, who know about the electric field effects of these states. So it's a very general question. At, n equals 200 or 150 for these states, the sensitivity to background fields may start to play a factor. But the fact that we still see the sharp, relatively sharp resonances, I guess the question is, do we think that that field mixing is stabilizing them and creating some of the width at this energy region? I suppose we can scale and see. We could actually calculate that. Yeah. So we've been using a delayed pulse and don't see much of a difference in the spectrum versus doing it in a DC field. But on the other hand, we haven't actually taken a lot of care to eliminate the stray fields when we think we have zero. How 0 is 0 for us is not on the standards of Frederick. So I'm curious if anybody has any comments about that.
Maybe an issue there is the quantum defect. So that if you have a quantum defect that is different from an integer, then you are somehow shielded from the effect of the field. So you would have to worry, particularly in the region where the calculations say your quantum defect approach is an integer value. And then there you have to be careful that your line width could be impacted by the field. And if you're away from that at n = 200, I don't think you have to worry too much.
I see.
I guess re-asking your question, perhaps more than answering it, I've always thought there's a little bit of an enigma with a lot of these states because to get to the extremely high angular momentum that's necessary to have a true heavy Rydberg state, the Stark mixing is your only access to that angular momentum. Yet, if you're well above the Inglis-Teller limit, you begin to lose all of your spectral resolution, at least in principle. And this is some sort of delicate balance between those that I've never really fully understood. If somebody does, I hope we'll hear about it here.
So thank you very much. I think we should thank Elizabeth again. And we now have an opportunity to stretch our legs, maybe see some of the sunlight outside, and we'll start again in half an hour. There's coffee in the back.